This video is for Calculus AB. This is one of the last examples in our notes we didn't get to during class. So we covered everything we need to here, and I hope maybe you've tried this one, thinking about your quiz coming up, but I thought I'd show you the solution of this one. Okay, so this tells us about the temperature of water in a tub, and this temperature is modeled by a strictly increasing twice differentiable function. Twice differentiable simply means that this function could be differentiated twice. In other words, there wouldn't be any sharp points or discontinuities as you find a first derivative, then a second derivative. Gives you some units there. It tells you that at time t equals 0, the temperature is 55 degrees Fahrenheit. Water is heated for 30 minutes. You can see in the table there. The first 20 minutes are shown in the table. You can see all the data up there in the table as well. Okay, so we're going to do Part A. Part A is not directly from our most recent material. It's definitely a good question, so I'm going to go ahead and do it. It says use the data in the table to estimate. It says show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in the context of this problem. So, estimating W prime of 12. So, of course, W prime stands for the rate of change or the derivative of W. And, of course, as is implied in the question, we don't really know what W is, and so we can't really exactly find the derivative, and that's why they use the word estimate. So the tools that we have for the job of estimating this would be the table, and of course, again, that's mentioned here as well. The phrase that I use in class, hopefully will stick with you, is this one. If you can't differentiate, that's fine. Just use the slope of the secant line. And that applies here because we can't find a derivative of W because we really don't know what W is. The best we can do is estimate it, and we'll estimate it using the slope of a secant line. And we are looking for an estimate for W prime of 12, so I'm going to use this interval here between these 2 points. The reason why I'm going to use those 2 points is because 12 is right between 9 and 15. All right, so I would then say that W prime of 12 is approximately equal to, the slope of the secant line would be 67.9 minus 61.8 divided by 15 minus 9. And I am coming up with a value of 1.017 for that. It didn't say, well, it does say use correct units when we interpret it, so I'm going to go ahead and put the units on here. The units would be degrees. There we go, degrees Fahrenheit per minute. All right, then it asks us to explain what that means. So what this means is what W prime of 12 means. I'll put it like that. So W prime of 12 is the rate of change of temperature in degrees Fahrenheit per hour when T equals 12 hours, or 12 minutes, sorry. So let me go back and fix my unit. Degrees Fahrenheit per minute. Okay, so this would be probably the most generic way of putting this. You could also say this. I think this would be a little bit better. You could say because W prime of 12, at least from our estimate, appears, well, actually we know for sure this is true because W is strictly increasing. Because W prime of 12 is positive, the temperature is increasing at a rate of 1.017 degrees Fahrenheit per minute when T equals 12 minutes. Something like that would probably be a little bit better. So a value and then an interpretation of what that actually means. All right, so now part B says use the data in the table to evaluate the definite integral from 0 to 20 of w prime of t dt. And then we'll also interpret the meaning on this one as well. Okay, so part B, we're supposed to evaluate the integral from 0 to 20 of w prime of t dt. Well, using our fundamental theorem of calculus, I would write this. This equals w of 20 minus w of 0, right? So the antiderivative would cancel out with the derivative, and then we would subtract the evaluations in the correct order. So according to the table, w of 20 is 71, and w of 0 is 55, and so that equals 16. So what does that mean? Well, remember that the definite integral of a rate gives you the net amount of change. And so I would say the meaning of this is the temperature of the water increased or changed, I guess you could say, by 16 degrees Fahrenheit from t equals 0 minutes to t equals 20 minutes. Something like that. You got to indicate that that 16 is a change in temperature. Using correct units, again, from 0 minutes to 20 minutes. All right, so then part C. Part C says for the interval from 0 to 20 minutes, the average temperature in the tub is given by that expression. Use a left Riemann sum with 4 sub-intervals indicated by the data in the table to approximate that. So let's go ahead and start right there, and then we'll answer the other questions. So we're using a left Riemann sum with 4 subintervals. So I'm going to say that 1/20th times the integral from 0 to 20 of w of t is approximately equal to, notice I'm labeling and writing down what this is supposed to be approximately equal to. And then my left sum would look like this. 4, getting that from the 0 to 4 right here. Whoops. And then I'm going to use the left side of the interval, so that'd be times 55. And then my next interval, here's my first one. Here is my second one. So now the base length goes from 4 to 9, so that's 5. Left side is 57.1. Now I'm going to go from 9 to 15, so now my base length is 6. Again, I'll use the left side, so it'd be 61.8. And then from 15 to 20, the base length is 5, times the left side, which is 67.9. Okay, so this is, I think I mentioned this before, but this is definitely a calculator active question. So if you're going to actually evaluate this completely, we would turn to the calculator and get 1215.8 is what it looks like. Okay, so then the question finishes with, does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. Okay, so we were told at the very start that this function w is strictly increasing. So that means it looks something like this. The graph of w would look something like that. And we used a left sum. So the left sum would use the left side of each interval. And so these left sum rectangles would all look something like this. So the way we would finish this is we would say the estimate is an underestimate because a left sum was used to approximate an increasing function or an increasing graph. as illustrated over here. So just a picture is not really a rigorous justification, but a statement like that off to the right is a rigorous reason for why the estimate is actually an underestimate. Okay, and then finally we get to part D. Part D says, for the interval from 20 to 25 minutes, the function W that models the water temperature has a first derivative given by W prime. So they still haven't told us what W is, but now they've told us, well, the first derivative we think is this, W prime, at least for 20 to 25. Based on the model, what is the temperature of the water at time t equals 25? So this is a net change situation. They're asking, what is the temperature of the water at time t equals 25? Well, we know what the temperature of the water is at t equals 20. We don't directly know how much the temperature has changed, and so I'm going to write it out like this. I know that when t equals 20, the temperature is 71. So I'm going to say that the temperature at 25, so I'll put W of 25 equals 71, which is the temperature at t equals 20, plus the change in the temperature that happens as you go from 20 to 25 minutes. So the way that we find the change in the temperature is to remember that the definite integral of the rate of change will give you the amount of change. And we know W prime is the rate of the change of the temperature. So if we want to find the change in temperature, we find the definite integral of the rate of change of temperature. So I'm going to write 71 plus the integral from 20 to 25 of W prime, like so. Please remember, as mentioned in class, this 20 and this 71 need to agree. They need to match. So 71 is the temperature at t equals 20 minutes. So at this stage, we would certainly use the calculator to evaluate that definite integral. And that equals approximately 73.043 degrees Fahrenheit. Okay, so I hope that went well for you. That's a nice review of a few concepts from 4.4 that we've been working on. Like I said, I hope it went well for you, and look forward to seeing you for your quiz.